Folks, welcome back. We're going to take a look at numbers 21 and 22 in Unit 3-1 here. So let's see, it says an archer shoots an arrow towards a target that is sliding in her direction. So this is about an arrow hitting a target. So let's start with this. We don't even really need the archer in here. We've got an arrow. Right, it's moving along. It has a momentum equal to mass of arrow, velocity arrow. This is going to be the first picture. Now, the target is over here somewhere, and it is also moving. I believe it's moving towards the arrow. Right? See this sliding in her direction at a certain speed. So it's got a momentum equal to mass of the target, velocity target. Again, this is still picture one because it's kind of like an instant in time. Now you notice that the arrow goes through the target, and then the target is stopped after impact. So right after the impact now, let's see, the target is stopped, it has a hole in it, and the arrow keeps going. So the arrow still has a momentum, mass of arrow, velocity arrow, picture two. So you draw your momentum picture, right? Snapshot in time before the impact, showing the momentum vectors. Snapshot in time after the impact, showing all momentum vectors. And the impulse picture, if I draw that, you got to think about the time frame when the arrow's like in contact with it. You know, the force on the target is to the right, but the force on the arrows to the left. The force interaction between these two is not a net force on the system if we define our system as both at the same time. And there are no other external forces, so there's no reason to think there's any sort of external impulse. So that's going to allow us to equate this momentum to this momentum and then write the equations out for it. It's virtually done. I'll let you folks finish that. Let's talk about this one now. Well, let's see here. So we got this person, Gail, running along and dives onto a sled that is initially at rest. So right there, let's just deal with this. Let's take this one step at a time. A person dives on a sled that's at rest. So we have a person diving. They are moving, no doubt. Yep, right there. So let's see, mass of the person, velocity person, picture one. Sled is just sitting here. Sorry about my super crummy picture, but after the person jumps on the sled, no doubt, the whole thing is moving now. So now we got mass. Let's put PS here for person and sled. Velocity, person and sled, picture two. Really crummy pictures there, I'm sorry. Anyway, now you can equate the total momentum in this picture to the total momentum in this picture. You end up with a pretty darn simple equation. Then they go down a hill 5 meters. And another person hops on. All right, so let's redo this. So now we're doing something like this. So this person's up on the top of a hill. There they are. So this is my picture two now. And they go down the hill. Here they are at the bottom. Wow, super crummy picture day for me. Here's picture three, and there's this other person there. Write a work energy theorem between 2 and 3 now to get velocity 3. And then when this person jumps on, here's a picture of the sled, and it's got somebody on it. Moving to the right, we'll just put MV3. This M is sled and person together. This person doesn't have a momentum. I'll put them in the picture though. Then both people are on the sled and it's moving. So let's call this, I'm going to call this capital MV4 or something like that. So you're going to have the momentum in this picture where this mass is the total mass here, sled plus person. And that's going to equal the total momentum in this picture, where this mass is the 2 people and the sled, and then times V4. So that should be enough to get you through that problem. Hope you're enjoying these momentum problems. Have a great day.